Hi everyone. My name's Mark and I'm joined with Ahmed, and this is the video for milestone one for the AI project. It's the single layer perceptron classifier and training simulator, and we're doing a car sales prediction model.
Hello, everyone. My name is Ahmed, and I will start us off by stating our goal of the project and what it really is all about. So, the main goal of our project is to predict whether a car would sell or not in the market. We designed a single layer perceptron in VHDL that simulates a real-world decision-making system used at secondhand car dealerships or even something like Auto Trader or Facebook Marketplace. The perceptron receives four input features, which are X1, X2, X3, X4, um, which are the pricing, mileage, reliability, and accident history, respectively. So the scale is 0 to 1, where a 1 indicates a good quality and 0 indicates a bad quality for all four X's. Each input is represented as a 8-bit signed fixed point number in Q4.4 format, scaled between 0 and 1, like I said earlier. And the output Y is a single bit representing whether the car sells or not. So Y equals 0 means it does not sell, and Y equals 1 means the car does sell.
This is the data set we used. There are six training samples in the training set and three samples in the validation set. So in the dataset, each row represents a car with ones and zeros describing its condition. For example, like the first example, a car with all ones indicate a car with a good price, a low mileage, high reliability, and no accident history. And therefore the car sells. That's why Y is a one. On the other hand, if it has poor reliability or a bad accident record, it's less likely to sell.
All right, so as for weights and bias update logic, at the beginning of training, all four weights and our bias were initialized to 0. The perceptron then updates these values using the standard learning rule given, which is W gets updated by W plus, or like our old W, plus the learning rate multiplied by the Y true minus Y predicted, mul multiplied by Rx. And our bias gets updated with our old bias plus learning rate multiplied by Y true minus Y predicted. And in this case, in both scenarios, our learning rate is fixed at 0.25, implemented by a single 2-bit rate shift.
And this is the step function and weighted sum. So the weighted sum, the perceptron first computes a weighted sum of the inputs, which is the sum of each weight multiplied by its x input, followed by the addition of the bias. This value is then passed to a step function that decides the output. If the sum is more than or equal to zero, the output is one, which means the car sells. If it's negative, the output is zero, meaning the car doesn't sell. So together, the weighted sum and step function form the perceptron's basic decision mechanism.
All right, so the best way to describe our design or architecture is this block diagram right here that we built, which is also on our poster. Starting on the top left, the box shown is the ROM or read-only memory and registers. It holds four things: our features, which are the X1 to X4, the label, which is our Y, our weights, and our bias. And then the data flows to the top right. Features, weights, and bias go into the MAC unit, which is multiply accumulate unit, which makes the weighted sum, given the formula written there. That sum then goes into activation. If the sum is positive, prediction is 1. If the sum is otherwise or just not 1, it becomes um, sorry, if the sum is positive, prediction equals 1, otherwise it's 0. And then now we can compare the prediction with the label. If they are different, the update block changes, the weights and bias just a little. Those updated values are written back to the registers here on the top left again. And in the middle is our control FSM. It selects trainer validate, picks the sample index and turns on update when needed. It also watches label and prediction to move to the next sample, advance epoch, and finally raise done when the whole loop is done. So that's the whole loop. It goes ROM or registers to the Mac, to the activation, to the update unit, back to the registers with the control FSM coordinating everything in between.
When doing this project, we faced a few challenges. The first one was managing the fixed point integer arithmetic and scaling. The second one was printing all the outputs during simulation to monitor the training progress. And the third challenge was aligning and integrating all the modules, like the data path, the update unit, and control FSM, so they worked seamlessly together.
All right, so to overcome these challenges, we use ChatGPT as a learning and debugging aid throughout the process. It helped us understand fixed point arithmetic and how to scale values between Q 4.4 and 8.8 formats. We also used it to structure and debug the test bench design and control FSM, and to print simulation outputs to track weights, weight updates, and convergence, as we're going to see shortly in the simulation. And ChatGPT also guided us on integrating all modules correctly and synchronizing the signal in our VHDL simulation. This allowed us to focus on everything else, such as understanding, testing, and refining our own implementation while learning faster.
And lastly, like our limitations in this project, one would be the fixed learning rate. If we use the learning rate right now, we use is 0.25, it's fixed. Using an adaptive rate could make learning faster in the beginning and more stable towards the end. Secondly, our inputs are binary, even though it's in Q 4.4, it's still either 0 or 1 in terms of value. And so if we use scaled or continuous inputs, the perceptron could learn more detailed distinctions between each car, and this would lead to more realistic predictions in the real world. And lastly, we used a small data set. A larger and more varied data set would help the model generalize better and make more accurate predictions for unseen car examples. And now it's time for the simulation. Run the project. We can see we have 1 second. You can see that we have 5 epochs starting here at epoch 0. We can see that between y predicted and y true, there are quite a few variations. And as we go on, so epoch 1, it changes a bit as the weights are updated. Epoch 2, slightly better. Epoch 3, that's when we see more similarity. And finally, at Epoch 4, that's when convergence happens. So there's no difference between the Y prediction and Y true, and that's where the model stops. And we have our finalized weights. If we look at the log here, we can see so all weights and bias start at 0, and we can see the process of how the weights update as we go through all the iterations. So here, and as we go through, it just keeps updating, and updating. And as we get to epoch 3, this is the last update. And it does epoch 4, finds out that everything's matching, and that's where the testing stops. Sorry, that's where the training stops, and then we begin validation. So as we carry out validation with the three test sets, we see that the y values are equal for all instances and validation passes. And here are the final weights and bias for the perceptron. All right, that is all. Thank you.
Thank you, everyone.